And our next speaker is Sandor Kruk from ESA. He's going to talk about Hubble Asteroid Hunter and exploring the ESA Hubble archive.
Yeah, thank you, Pascal, for the introduction and for the organizers for running this online conference so smoothly and for giving me the opportunity to present the work that we've been doing last year at ESA. So it's really great to see a whole session dedicated to citizen science at ADAS. So talking about asteroids, I hope to convince you that archival data is extremely valuable and that you can discover many treasures in the data if it is mined properly. And what better tool there is for data mining than the human eye? Through the combined efforts of thousands of people. So this work on the Hubble Asteroid Hunter, exploring the Hubble archives with citizen science, would not have been possible without my colleagues shown here, in particular Pablo Garcia Martin and Bruno Merin from the ESA Science Data Center. And of course, the 11,000 volunteers in the project itself. So our main motivation for this project is to facilitate the discovery process in space science missions and to better explore the rich Hubble archives. And in fact, most of the publications nowadays from the Hubble Space Telescope are either archival or partially archival, as you can see from this plot. So we are now slowly moving in this era of data-driven astronomy, where the majority of science is done with surveys and with archives. And in the 30 years of observations, Hubble produced hundreds of thousands of spectacular images of rich clusters of galaxies, of nebulae, places where new stars are born, but also where massive stars die, such as this gorgeous image of the cosmic reef here in the center of the image. But occasionally, these nice images made by Hubble that you see are ruined by objects much closer than the targets Hubble was observing. And you can see in this nice long exposure of the Hubble parallel fields of galaxy cluster Hubble 370, 20 streaks made by asteroids situated in the foreground. So actually in this image, there are a total of 7 asteroids numbered from 1 to 7. And the reason why the asteroid appear multiple times is that it moves between 2 consecutive exposures of Hubble. So this is a long exposure of Hubble. And the trails that you have seen have this exceptional characteristic. So they appear curved in the Hubble images. And the reason for the trails being curved and not straight, as perhaps one would expect, is because of the parallax introduced by the motion of Hubble around the Earth. So typical exposure of Hubble is 20 minutes, whereas Hubble goes around the Earth once every 90 minutes, which is enough to imprint this smooth displacement in the shape of the trails. And it is easily resolved by the high resolution imaging of Hubble. And multiple images of the same asteroid can appear in the image because Hubble usually takes consecutive exposures. And once upon a time, actually, some astronomers called these asteroids in these images the vermin of the sky because they interfered with the observations. But asteroids are amazing objects to study on their own. They are the leftover from the formation of our solar system some 5 billion years ago and contain information about its origin and the pristine material that existed back then. There are over 1 million asteroids known now. Most of them are in between the orbits of Mars and Jupiter in the main asteroid belt. But some of them get displaced and can move closer to the Earth, and we call them near-Earth asteroids, which are of course rarer, but much more important because of the remote possibility that they might be colliding with the Earth in the future. So the motivation for our citizen science project is to identify the asteroids in the Hubble images and to characterize them. So for this purpose, we built a citizen science project based on the Zooniverse project builder. And this project builder allows us to build projects quickly through a friendly interface and to promote the project on the Zooniverse platform to a large pool of volunteers. So this is the main interface of the project, accessible at the following link. And what we are showing people or volunteers are composite or drizzled images from the Hubble Space Telescope, the Advanced Camera for Surveys, and Wide Field Camera 3. So the data taken by Hubble in the last 20 years. And since the images were quite large to inspect in one go, considering how small these trails are in the images, we split the images into 4 different quarters, like the one you see here. And this is what we show to the volunteers. So the volunteers had to answer a simple question whether an asteroid is present in the images or not. And if it is in the images, then mark the beginning and end position of the trail so that we can identify them and we can convert them to astronomical coordinates. So we launched this project just ahead of the International Asteroid Day on the 30th of June, 2019. And we distributed, the project was advertised widely in the ESA social media channels and also on Zooniverse, and it gathered tens of thousands of classifications in the first days. And actually, there was a significant increase in participation during the lockdown in April this year, when people had to stay home and were looking for new things to do. So citizen science projects were indeed a good scientific and educational resource for people. For example, many teachers use Zooniverse project as an online resource. But it's also a place where people can look at nice images from the universe, as you can see from the reaction of this volunteer, saying there are lots of beautiful sights in the universe, especially now that I can't travel to see any earthly sights except those in my immediate neighborhood. Now, in total, we had 11,000 volunteers, over 150,000 images classified, and 2 million classifications during 1 year. And here's a plot showing all the volunteers in the project and their contribution, with the size of the boxes corresponding to the number of classifications. There are a couple of super users, we call them, who classified many of the images. By using the volunteer classifications, we identified the images where more than half of the people said there were trails present. And with the science team, we inspected the images. Now, the reason for further investigating these images is while we're used to the beautiful Hubble images on the internet, those are processed images. So the original images contain artifacts, which can be confused with asteroid trails. For example, occasionally images have these badly subtracted cosmic rays or arcs from gravitational lensing effect that is targeted in many Hubble images. And these resemble asteroid trails. There are also satellite trails that cross the entire image. And these are satellites in higher orbit than Hubble. So we inspected the classifications and identified 1,500 good asteroid trails, like you see, like the one you see in this image. With the yellow point, you can see the individual markings of the volunteers. And with the white circle, you can see the aggregated marking using the clustering algorithm HDB-scan. And here are some more examples of the trails that the volunteers identified in the images and the markings. They have this crazy shape. Some of them are curved, some of them are S or C shaped, depending on the motion of Hubble and of the asteroid. And you can actually recover these asteroids moving in the roll frames as well, after we identify them. And quite early on the project, one of the volunteers, Melina Teveno, found this nice asteroid trail photobombing the Crab Nebula in a rare cosmic coincidence. And she created this nice color image of it and sent it to us. Some of the volunteers also found this nice image of a dwarf galaxy and 2 asteroids crossing paths in the foreground, which again is pretty rare to have 2 asteroids along the same line of sight at the same time, like in this image. And many volunteers went beyond simply classifying images. The project has an active forum where people can go and post nice images, ask questions to the science team, and even do their analysis. In this example, one volunteer explained the process in which they identified the asteroid in the image themselves using ephemerides from the Minor Planet Center. So going on to some results, in total, out of the 1,500 trails, we identified 500 known asteroids based on the ephemerides in the Minor Planet Center database. So this is the largest database of small bodies. So these are asteroids that match their predicted position within 3 arc minutes. You can see some examples here on the right-hand side. Most of them are main belt asteroids and have magnitudes between 20 and 24, so they're pretty faint. Now, one of the biggest advantages of Hubble is that it is sensitive to fainter asteroids than instruments from the ground. But still, about 1,000 of these objects are unknown objects, or objects which have a large orbital uncertainty. So it is entirely possible that these are new objects. Since Hubble, as I said, is sensitive to small and fainter objects. And we think that there are thousands of asteroids, especially in the main belt, that have still not been discovered. So we are further scrutinizing the classifications. And since we know the orbital parameters of Hubble, the shape of the trail can tell us about the distance to the asteroid based on the parallax. And this is still something that we're working on to identify the missing 1,000 asteroids. Now, one of the biggest advantages of having people look at the data is that we can benefit from the power and intuition of the human brain. When we first designed this project, we did not realize that the strong gravitational lensing that were imaged so frequently by Hubble, this phenomena, these small distortions in tiny arcs caused by the bending of light around massive objects, can sometimes throw people off, the volunteers off, and they identify them as asteroids because they look like curved trails. So they were asking, what are these objects? A few weeks into the project, we asked the volunteers to tag these objects as gravitational lenses so that the science team can filter them out when we analyze the results. And when we analyzed the results this summer, surprisingly, we realized that we found 200 new gravitational lens candidates. Some of them you can see here on the right. I call them candidates since they have to be confirmed spectroscopically. And these were not targeted observations, but serendipitous findings. And this is great, since so far only about 1,000 strong gravitational lenses are known. And this serendipitous discovery would probably not have been possible with automated methods, or perhaps even by astronomers, since we would have probably ignored them if we were looking for asteroids. Now, another surprising discovery is that a small but non-negligible fraction of the Hubble images contain satellite trails that go across the entire image. So you can see here on the right-hand side an example of a broad satellite trail that is out of focus, probably a satellite that passed quite close, tens of kilometers away from Hubble. There are also satellites that are flickering, or satellites further away, possibly on the way to a geostationary orbit, showing the same parallax effect as for the asteroid trails. And also an image with 3 satellites. And we can work on this exercise and perhaps worry that in the future, the number of satellite trails will only grow and impact the Hubble observations. So the satellite trails not only impact ground observations, but also space observations in low Earth orbit. And finally, if I have 1 or 2 minutes left, I would like to advertise some ongoing work that we've been doing in collaboration with Google. So we have been using their object detection algorithm, AutoML, trained on the volunteers' classifications to automatically detect asteroids and satellite trails in the images. Now, in the last few years, there have been many advancements in computer vision with deep learning algorithms based on convolutional neural networks that are not only able to classify objects, but also detect their positions. Such as this object detection algorithm being able to identify cars and people and traffic lights in the images. So we applied this algorithm to the Hubble images, and we're able to detect the asteroid trails with a precision of 80% and a completeness of 60%. And using this algorithm, we classify the archive, finding new asteroids and satellite trails in the Hubble images that people either have missed them or they haven't been shown a certain data set. Now, with the Google AutoML, we were able to train the algorithm in only 3 hours of world clock time and classify the entire archive in just 7 hours. So only in 10 hours in total. A task which has taken the volunteers 1 year in total. It took us 10 hours. But of course, we already had very good labels for training for 4 different objects. So asteroids, satellites, cosmic rays, and gravitational lens arcs. If you want to hear more about this project, automatically detecting asteroids in the images, you can follow this link here on the right. So some takeaway messages. Look at the data if you can. Sometimes unexpected things might hide in there. We went to search for asteroids and found gravitational lenses, satellite trails, but also some other unusual morphologies like collisional rings that I didn't have time to talk about. The next take-home message is that one astronomer's trash can be another one's treasure. Hubble, with its small field of view, was not designed to observe asteroids, but the fact that it is in space and can reach fainter magnitudes can offset this. Thirdly, citizen science has proven to be an efficient method to explore large data sets, as me and others have shown during this session. Now, there's just something about the human brain that is able to go beyond what is required and spot unusual things in the data. But at the same time, like you've heard probably many times at ADAS already, with upcoming missions such as Euclid and LSST, data will increase exponentially, but humans will not. So we need humans and machines to work together in the future. And we need artificial intelligence methods to scale up the power of crowdsourcing. And for this, we need many and good labels to be provided for by the citizen scientists. Thank you.
Thank you very much, Sandor. And we have already 2 questions. One question is, can you find slow-moving trans-Newtonian objects?
Yes, so these are actually harder to find because the exposure time of Hubble is only 10, 20, 30 minutes. So it's not very long, and they don't produce such a long trails in the images. As I said, most of the trails that we identify are from main belt asteroids.
Okay. And another question is about the Asteroid Hunter project. You mentioned super users. Do you know who are the super users? What age, what occupation? Is there a certain type of people for super users?
It's varying actually. So we are in touch with the super users because they obviously classify a lot. They comment a lot on our project forum talk, and it's actually a range. So I'm collaborating now, for example, with one of the super users who is about 70, and he's a retired engineer in Paris. So it's actually, yeah, as I said, a wide range, but people who are really passionate about it, and they go beyond the scope of the project. So they don't only classify, but they actually go on and use different surveys. They look into SIMBA, they look into NET, and they are actually, I would say, expert citizen scientists.
Okay, thank you very much.